you're right. Just get 4K TVs and stack them next to each other. But then you get bezeling, which, is no fun. Okay, any questions about anything course related before we kick things off today? Today's going to be kind of an easy and fun lecture, I think, because we're going to talk about noise. And we've got our beautiful, here the floating dust particles represent the noise in the signal. My goal here is that every lecture will have an animated title slide that is a metaphor for the topic itself. So here's this. Yeah, it's that production value, man. You guys paid good money for this. So, all right. So today let's talk about noise. So, our learning objective for this lesson. In this lesson, we will look at multiple types of noise signals and how they may be implemented in Python. So, pretty easy. But we're going to learn I learned some stuff about noise preparing for this lecture. So here's our outline. We're going to talk about a handful of different types of noise. We're going to talk about uncorrelated noise, Brownian noise, pink noise, and Gaussian noise. And we're going to talk about this concept of integrated spectrum, which I think is pretty cool. And it gives us a really good sort of insight into the behavior of, our noise, right? Because if you just look at a noise waveform, it can be kind of not obvious what kind of noise you're looking at. But if you look at the integrated spectrum, you can actually sort of see the characteristics of the noise. So let's just jump into it. Let's talk about uncorrelated noise. Dang, you know what? I just realized I didn't do any of the animations. You're just getting that raw black and white slideshow, guys. I apologize. All right. So what is noise? In the context of signal processing, there are two meanings of the word noise. So the most popular one, right, is the first one, an unwanted signal of any kind, right? Anything that is not the signal that you're trying to send or receive is noise, right? Anything that's bad is noise. This might even be, a malicious sort of signal, right? A signal that is being used to jam your signal or disrupt your signal. That could be considered to be noise as well. But noise for this class, for this lesson in particular, we're going to think about the second meaning of noise, which is a signal with a spectrum that contains components at so many frequencies that it lacks any consistent harmonic structure, right? We saw before that, we can build signals and we can look at the structure of the signals and make observations about what that signal is by looking at its harmonic structure. Noise is a signal that's got so much frequency nonsense going on to it that it has no cohesive harmonic structure. It just looks kind of crazy. Although, that being said, we can still look at the spectrum of noise and make some observations about noise. Uncorrelated noise. The simplest kind of noise to generate is what they call uncorrelated uniform noise. So let's unpack those two adjectives. The first one, uniform, random values from a uniform distribution. That means that every value in the range is equally likely to be present. That means that across whatever frequency range you're looking at, any particular frequency component, any harmonic is likely to appear in any place as it is in anywhere else, right? You're going to get a completely sort of flat, uniform distribution. And then uncorrelated, the values are independent of each other. Knowing one value provides no information about the others. And as we'll see in this lesson, there actually are some types of noise that are correlated, where whatever the previous value of the signal was does in fact affect what the next value is. We use a more common name for uncorrelated uniform noise because it's sort of a mouthful. We call it white noise, right? We call it white noise because it occupies the entire spectrum sort of evenly. Right, if it was light, it would just be white light. So that's why we call it white noise. So let's unpack the class, the code for writing uncorrelated uniform noise. And basically, here you can kind of see that, in the evaluate function, our values for our signal is just np.random.uniform minus self.amplitude to self.amplitude, and the length is the length of the signal. np.random is that NumPy random function that just generates values from a uniform distribution. So basically we're saying just start generating random values again from a uniform distribution and sort of bind them to the lower limit needs to be whatever the negative amplitude that you set was and the positive amplitude that you set was. And so you can sort of define the range of amplitudes for your noise signal, but as far as where those points are going to appear in your signal, totally random, and that randomness is based on a uniform distribution. So they can appear at 2 or -3 or wherever with equal distribution. So let's see. Moving on to the next one. So now if we want to actually go ahead and do it, the code here is the signal equals think DSP dot uncorrelated uniform noise, and we go ahead and make a wave using the signal.make wave function for ½ second at our standard frame rate here of 11 kilohertz. And so if we plot both of these signals, I went ahead and ran it twice, and if you sort of stop and take a beat and sort of look at these individually, you'll see they are different, right? So sort of if you back away, it's like, well, this guy look the same. They all look like noise, right? If you sort of zoom in and take a closer look at it, you can see that, yeah, they're different, right? They're entirely different waveforms. Again, they're totally random. And I even included, I'm going to surprise everyone who's not really paying attention and has their headphones on really loud. No, it didn't work. Play my audio, you jerk. Yeah, there we go. So we know it to be static. So uncorrelated uniform noise, white noise, is basically just static. So let's go ahead and take a look at the spectrum of our uncorrelated uniform noise, of our white noise. Spectrum equals wave.make spectrum. But here we're going to use the plot power function instead of the just regular plot function. It's exactly the same as spectrum.plot, except it uses power instead of amplitude. And in this case, power is just equal to amplitude squared. Yeah, so that's all it does. So when you view the waveforms, you're going to get basically the same sort of, or when you view the spectrum, you get the same sort of thing. So if we view the spectrum of both of those signals that we created, again, you can see that it's, again, they're different from each other, even though it was the same function that created them. And there's really no rhyme or reason, right? If you sort of look at 0 and you look at 5,000, it's clear that there is no bias one way or another. There isn't more low frequency than there is high frequency. It's uniformly distributed throughout, right? There's peaks, right? There's some stuff that happened, a lot, these higher frequency components, but there's no method to that madness, right? These big peaks here are different than these peaks here, and they're sort of evenly spread out throughout the signal. So, are there any questions about this uncorrelated uniform noise or this white noise? So white noise is the most boring of the noises. So let's talk about characterizing noise. When attempting to characterize signal noise, there are 3 important things that we gotta look at. So when we sort of, like I said, when we want to sort of make observations about noise, there's 3 things that we're going to focus on, 3 things that we're going to look at. The first one is the distribution. In a random signal, it's a set of possible values and their probabilities, right? In that white noise, the distribution was uniform. Another example that we'll see is this. It's Gaussian noise, right? The set of values is the range from negative to positive infinity, but values near 0 are the most likely, with probabilities that drop off according to a bell curve, right? So the signal is going to be sort of centered around 0. It's not entirely uniform, but it has some distribution, right? We might see distributions that favor low frequencies or high frequencies or something like that. But the distribution is like where, if we look at the spectrum or if we look at the signal, where is all of the signal sort of falling into? Is it uniform? Is it centered around 0? What's going on? What is the distribution of that random signal? The second one is correlation, right? Is each value in the signal independent of the others, or are there dependencies between them? The next one we're going to look at here is called Brownian noise, which says that each value of the signal is the sum of the previous value and some random step. We'll talk about that in more detail here in a minute, but the next value in the signal is dependent on the value of the signal that came before it. It's not entirely random. So, is there a correlation between values in the signal? Are they completely independent, right? In Brownian noise, they are dependent on each other. In white noise, they're completely independent of each other. So what is the correlation between values in the signal itself? And then finally, probably the most important is this, the relationship between power and frequency. there's two examples here. The first one is white noise, that uncorrelated uniform noise that we looked at. And here, the power at all frequencies is drawn from the same distribution, right? 1 hertz is just as likely to appear as 5 kilohertz in the spectrum. There is no relationship between power and frequency in white noise. But if we look at what they call pink noise, then power is inversely related to frequency, right? There's more noise at the lower frequencies. And as we move from 0, that distribution gets smaller and smaller. So there will be more power at 10 hertz than there will be at 5 kilohertz. There actually is a relationship between power and frequency. So just to kind of recap those, the 3 important things, here's your test questions, right? The 3 important parameters to characterize signal noise are distribution. What is the set of possible values for the signal? The correlation, are the values of the signal dependent on the other ones, or are they independent of each other? And then what is the relationship between power and frequency in that noise signal? Any questions about those 3 characteristics? All right, moving on. Let's talk about integrated spectrum. So, integrated spectrum is a function of frequency that shows the cumulative power in the spectrum up to that frequency. You can think of it as, it says right here on this bullet point, it's a great way to visualize the relationship between power and frequency. So if I click all the way back here, this really doesn't tell us a whole lot of information about power versus frequency. I mean, we can kind of see that it's sort of uniformly distributed, but we don't really know that for sure. Integrated noise gets us a bit of a better plot. So we can do that by taking the spectrum. So when we've created a signal, we've created a wave, then we've created a spectrum, we can take that spectrum and do dot make underscore integrated underscore spectrum, and then plot the integrated spectrum, and we'll get something like this. So for that uncorrelated uniform noise, you get an integrated spectrum that looks like this, a sort of vertical linear line that goes up from 0 all the way across, right? That sort of shows us that the spectrum is evenly distributed across frequency. Right? There really is no relationship between frequency and power here, right? It all kind of builds on each other. So one of the things that I'll be sort of looking for you guys to be able to do on the test is I'm going to show you what's the y-axis. Y-axis is, is power level. So you can think of, and remember it's cumulative, right? So we add it up as we go, and so at the beginning there's very little power, but by the end it's all the power, right? We've added up all the power by the end, so we get to 1 by the time we reach the end of our spectrum, but it's adding it all up as we go. So we can kind of see, you can think of, so was it you, Akil, the other day that was asking, we were looking at spectrograms and saying, was it the rate of change or anything like that? You can almost view this as the rate of change of power to frequency, right? So it's sort of constant. It's a constant line, and it's never really going to change. So this shows us, by looking at this, we can say, it's sort of evenly distributed, right? If I start ramping up or ramping down, then there would be a relationship between power and frequency. But here, for white noise, we just get a blank line. And like I said, a great, you can definitely count on in the test. Slope isn't power, so Curtis asks, so slope is power? No, the y-axis is power, but the slope is the relationship between frequency and power. So the fact that this signal, this noise, has a constant slope relatively, it's got a little bit of wiggle, but there's some basically constant slope, means that it's a uniform relationship between power and frequency. I love it when it's you see someone is typing for what feels like forever, and then they just say, okay. So much anticipation, and then it then it falls away. Okay, but anyway, yeah, so that's what we're going to do is, like I said, you're going to look at integrated spectrum. That's going to tell you the characteristics of the noise that you're looking at. Like I said, one of the things you should be expected to do on the test is, let me show you a picture, let me show you a plot like this, and you tell me, oh, that's white noise, or that's Brownian noise, or that's, you know, whatever. All right, speaking of Brownian noise, let's talk about Brownian noise. So Brownian noise, the definition here is each value is the sum, each value of the signal is the sum of the previous value and a random step, randomly up or randomly down, right? It's named for this concept in physics called Brownian motion, in which a particle is suspended in a fluid, moves apparently at random due to unseen interactions with the fluid, right? The sort of most famous version of this experiment is you take like a really tiny seed and you drop it in a glass of water, and if you watch it, you'll notice that it sort of like moves around in like this sort of random fashion. And the reason it's moving around is because the seed is so small that the force of the water molecules hitting it is actually pushing it around, right? It's not the current of the water, it's the actual molecules hitting it that are pushing it around. And because the molecules are sort of flying around at random, it sort of randomly seems like the sort of seed is moving there. So that's called Brownian motion. And so Brownian noise is kind of the same deal, right? And a random walk is a mathematical model of a path where the distance between steps is characterized by the random distribution, right? So whatever step you're at, you're going to choose a random number, you know, positive or negative, or, you know, +2 or -3 or whatever, and you're going to go to that next one from the previous step, which means that Brownian noise is correlated noise, right? Because this next step of the signal is dependent on the previous value of the signal. So in a one-dimensional, so is the step constant? No, the step is random. And that's so Edward asks, is the step constant for each value calculation? And no, the step itself is what's random. So in a one-dimensional random walk, the particle moves up or down by a random amount at each step. So at every step, you recalculate, you rethrow your dice, right? You get your new random number, and that whatever that value you get is going to be what you change to. So the location of the particle at any point in time is the sum of all the previous steps. So you add up all the steps, and you're going to get the value. So let's take a look at how Brownian noise is implemented in Python by looking at its evaluate function. We start by dys equals np.random.uniform minus 1 to 1, length of t of s. So here we're actually getting our random steps, right? We're getting a collection of steps between -1 and 1 for each value of the signal. And then cumulative sum, we're going to add them all up, and that gets us our actual signal itself. And that makes sense, right? Because if you go, say our sequence is, 1, 3, -2, right? By adding up all those signals will get you where you ended up at, right? So that's why we add them all up in cumulative. So the first one is by itself. The second one is the first one and the second one added together. The third one is 1, 2, and 3 added together, and so on and so forth together. And then finally, you've got to normalize, because we want to still keep the noise within the bounds of an amplitude, right? We still don't want the signal to go over, +1 or -1. So we're going to normalize it to the amplitude to keep it from just shooting past whatever our desired amplitude for the signal is. And then we return those values. Any questions about the implementation of the Brownian noise class? Okay, so let's take a look at what it looks like. The code to sort of plot it is, signal think VSP dot Brownian noise. We're going to make signal, same deal, duration in ½ second, frame rate of 11.025 kilohertz, and then plot it. And we get stuff that looks like this. So here is the noise signal itself. So here's two, I ran them back to back. So we get two signals that are different from each other. They're very different from each other, but notice the difference between it and the white noise is they're closely tied together, right? The next value isn't far away from the previous value. So you still get this kind of noisy, sort of messy looking, almost cohesive signal, despite the fact that it's still noise. So you can't get values that jump over all over the place. They're sort of tied together inside, inside each other. So, any questions here? People are typing. completely forgot to do a plot of that. I'm so sorry. Now I want to know what it sounds like. Let's do it. You guys want to figure out what it sounds like? All right. Did you say nah, Max? Now we're definitely going to do it just because Max doesn't want to do it. Let me get that. All right. Give me like 2 seconds to pull up VS Code. Find a place where I put the... Here, here. It's called brown.py. All right. Chill out. Communist noise. All right, here we go. Let's see. Import think DSP. Let's go and plot it just for fun. Matplotlib. .py plot as PLT. Now let's do the thing. Signal equals think DSP dot Brownian noise. Wave equals signal dot make wave. Let's do a long one. Duration equals, let's do 2 seconds. Let's leave it there. Wave dot play. And wave dot plot plt dot show. So plt dot show. All right, give me that plot. Let's see. Well, that didn't sound like anything. That's disappointing. I don't know why I thought it would be weirder than that. And it's playing, but... Can you guys hear it? Well, that's disappointing. It sounds like very quiet. I mean, it's. I mean, in fairness, it is really quiet. Like, there's not. It sounds like. Maybe that's. Yeah. It's like it's not as harsh as white noise. Like white noise was like in your face, but this red noise is like it's almost soothing. Yeah, you could like fall asleep to this. It's like ocean waves. That was nice. It was very soothing. All right. Boom. So that's Brownian noise. Okay, so we got the waveforms. They look like that. And as we saw, it sounds like a much nicer version of white noise, whereas white noise was pretty like harsh and kind of blasting in your face. Brownian noise was like calm, gentle ocean breezes. And the reason for that is, let's take a look at the spectrum. So if we plot the spectrum of our Brownian noise, notice that like almost all of the frequency content exists like here at these very low frequencies, right? It's a very low frequency signal. So much so that I even had to like zoom in to like just 0 to 100 hertz to be able to see anything. So it's very, very low frequency content, very different than the white noise that had spectrum all over the place. And if we look at the integrated spectrum, remember that the white noise had just like a flat line, right? Sloping linearly up from 0 to 1 at the maximum frequency. But here, Brownian noise has like it shoots up almost initially, like right off the bat, and then basically just stays flat forever. So like almost all of the frequency content here, by looking at the integrated spectrum, is in these low frequency, is in this low frequency range. Which is also probably why it sounded much more soothing than white noise, right? Because it was low frequency noise, which means it's sort of low, gentle humming, as opposed to white noise, which just sort of blasts you with all kinds of stuff. And yeah, as was talked about in the chat, Brownian noise is also sometimes called red noise. And this is because it's a analogy to light, right? The majority of the power is in the lower frequencies. Just like light, red is on the lower frequency spectrum of visible light, so that's why they call it red noise. No, it's not a reference to communism. And in fact, we can actually define a function for red or Brownian noise here, where power is equal to e to the k, where k is just some random constant, over the frequency squared. Right? Don't get too hung up on the e to the k bit. Just know that power is inversely proportional to the square of the frequency, which is why, as we came back here, right, all of that frequency content is right there in the very beginning, and then it drops off right off the bat. So it's inversely proportional to frequency squared. Any questions about red noise? All right. So one thing that's kind of useful sometimes is to view the log of the spectrum, right? Because the spectrum basically exists only in that low frequency space and just ramps off so fast. If we plot the log of the spectrum, then we get something that makes a little bit more, I don't know, it's more reasonable to look at, right? So we have a lot of frequency content at the very beginning, and you see it sort of start to fall off as we go to the lower frequencies. So as we get out to 10 and then 100 and then 1,000, we can see it sort of slowly start to ramp off. So viewing the log of the spectrum can sometimes be a little bit more interesting to look at than just viewing the straight up spectrum plotted directly. All right, so that is red noise. Next up is pink noise. And you could probably guess what pink noise is. As the name suggests, pink noise is like red noise, but with a little bit more power at the higher frequencies, right? So if I go back here, right, if red noise is all the way over here at the lowest end of the spectrum, then pink noise is still pretty low, but is kind of, over just a little bit, right? It's not quite as low as red noise. And their functions are very similar to each other, right? Red noise's power is proportionally inverse to the frequency squared. That is a major typo. Hold on. 23. Right. If red noise is P is equal to e to the k over frequency squared, pink noise is equal to e to the k over frequency raised to beta, where beta is somewhere between 0 and 2, right? So it's still going to fall off exponentially. It's just going to fall off a lot slower than the red noise will, according to frequency. So, like I said, red noise is basically the same as, pink noise is basically the same as red noise. It's just sort of going to fall off a lot slower. There's a class for pink noise, which basically just has you define a term beta in addition to the amplitude. Now, if we go ahead and plot pink noise, we get a thing that kind of looks like this, which sort of makes sense if you think about it. If I go back and click all the way back to red noise, our Brownian noise, right? We get a sort of random walk looking thing here, but everything is sort of tightly packed together, right? Which is to say that there's less high frequency noise on the signal. But if I go and look now at our pink noise, you can still kind of see the random walk business happening, but there's a lot more high frequency noise happening in this signal, right? So there's more high frequency. And in fact, when we go ahead and plot the spectrum, again, you can see most of the power content is still kind of over in the lower frequencies, but it's not quite as stark. We can still see frequency content coming off at 1,000 hertz and 2,000 hertz and 3,000 hertz. Even at 5,000, we can still visualize some frequency content, some power content happening right here. So it's not quite as intense, right? Which makes pink noise sometimes more favorable, right? You still get the kind of low frequency noise effects that you're looking for, but it's not quite as intense, right? It's like softer, it's less abrasive than red noise is. And when we look at the integrated spectrum, you can still kind of see the same thing here. It's got a similar structure to the red noise, but that slope is much more gentle than it was for the red noise, whereas red noise was basically like, bam, we're up here at 1, and then we just go over like a tabletop. Here it sort of gently slopes over to the higher frequency ranges. So that's pink noise, like red noise, but not quite as intense. If red noise is communist noise, then pink noise is just like socialist noise. Not to get political the day before an election. All right. So, pink noise is the Bernie Sanders of noise. All right. Any other questions about pink noise? All right, the last one I'm going to talk about is called Gaussian noise. Now, sometimes white noise is often used to mean uncorrelated Gaussian noise, right? And in fact, as you're going to see, they're very similar to each other. And if you're going to look at the spectrums for white noise and Gaussian noise, they're going to look basically the same. If we define it, the signals are going to come from, it's still a random generation of signals, but now they come from a normal distribution as opposed to a uniform distribution, right? So when we plot the signal, again, it kind of looks basically exactly the same as white noise, but it's tamped down. It's not quite as all over the place. It sort of is still kind of grouped around. You can see that it's thicker around 0 than it was in the white noise. The spectrum itself, though, looks like it's all over the place, right? Because even though the values are tied closer to 0, the spectrum is still kind of all over the place, which is why Gaussian noise is still sometimes called white noise. And if we plot the integrated spectrum, you can see it still looks basically the same, right? The distribution of frequencies themselves are still a lot more uniform. Yeah, that's really all there is to say about Gaussian noise. So you can think of uncorrelated uniform noise and red noise being like the more intense, more extreme versions of the noise, whereas pink noise and Gaussian noise are like a more calmed down version of their respective noise types. So there we go, man. That is it for today. We kind of burned through that real fast. I guess it goes faster when I'm not typing the code. So just to recap, we talked about uncorrelated noise, integrated spectrum, Brownian noise, pink noise, and Gaussian noise, right? And really the only things I need you guys to do here is just be aware of the differences and be able to recognize the characteristics, right? So if I, for example, if I show you this plot on the exam, say, oh, that's pink noise, whereas, that is red noise, right? And the difference there is red noise is more of like a tabletop, whereas pink noise is a more rounded curve, whereas white noise is a straight line. So those are the sorts of things. You need to be able to characterize those different types of noise. And the ones, again, we're going to worry about white noise, red noise, and pink noise. I don't think there's any such thing as like blue noise or purple noise or anything like that. So, here we go. Any questions about any of that? All right, gang. Well, we are done with plenty of time to spare. So, if there is no other questions, we'll go ahead and leave it there. Don't forget that you have an assignment due on Wednesday, and we're just going to kind of keep chugging along with this material out of the book. So, if there's nothing else, yeah, I'll see you on Wednesday. Don't forget to go vote if you haven't already.